Look up at the night sky and you'll notice that stars are not just tiny, bright points of light. They're a mesmerizing blend of different colors: red, blue, yellow, and sometimes even white. But what exactly causes these variations in color? It's a fascinating dance of physics, light, and stellar ingredients that makes every star shine in a unique hue. Let's dive into the stellar world and explore what makes them so colorful. Grab your telescope, or, if that's too much work, just grab some popcorn. This is going to be an astronomical ride. Star colors, a product of heat and age. You might think that stars are like those mood rings from the 90s, changing colors depending on their mood. In a way, you're not entirely wrong. Stars get their color primarily from their surface temperature. The hotter the star, the bluer its color, while cooler stars shine in red or orange hues. For instance, Betelgeuse, a red giant, has a surface temperature of about 3,500 degrees Celsius, making it cooler compared to a blue supergiant like Rigel, whose surface can reach up to 20,000 degrees Celsius. These temperature differences are due to variations in the rate of nuclear fusion within each star, where higher temperatures are associated with rapid and intense fusion. The color spectrum of a star is essentially a cosmic thermometer, allowing astronomers to estimate a star's temperature just by observing its color. So the next time you see a bright blue star, just know it's showing off its cosmic heatwave. The stellar spectrum, reading a star's DNA. Stars emit light across the electromagnetic spectrum, from the visible range to infrared and ultraviolet. Spectroscopy, the study of how light interacts with matter, allows scientists to determine a star's composition, age, movement, and even its potential future. The light emitted by stars can be split into a spectrum, which shows characteristic emission and absorption lines. Each element has a unique fingerprint of bright or dark lines, which helps astronomers determine what elements are present in the star and in what quantities. Through this analysis, astronomers have found that stars are mainly composed of hydrogen and helium, with trace elements such as sodium, calcium, and iron. Spectroscopy helps us understand everything from a star's temperature and density to its movement, offering a direct look into the star's life cycle. Spectral classes, from hot O types to cooler M types. Stars are classified into spectral types, ranging from the very hot O-type stars to the cooler M-type stars. O-type stars are often blue and are the hottest, while M-type stars are red and much cooler. If we could give them personality traits, O stars would be the energetic teenagers of the cosmos, glowing brightly and burning out quickly, while M stars are more like wise old folks, taking things slower and lasting much longer. These spectral classes are used to group stars based on their temperature, luminosity, and color, which gives astronomers a standard way to compare and study different types of stars. For example, a B-type star is hotter and bluer than our G-type sun, but not as hot as an O-type star. This classification system helps map out the diverse population of stars in our galaxy and beyond. Main sequence stars, the average Joe of the universe. Main sequence stars, like our Sun, are the backbone of the cosmos. They shine thanks to nuclear fusion in their cores, converting hydrogen into helium. The energy produced by fusion not only prevents the star from collapsing under gravity, but also defines its temperature and color. Main sequence stars come in a wide range of colors depending on their mass and temperature. Our Sun, for instance, is a G-type main sequence star, producing a yellowish light, which is why everything on Earth has a warm glow during the day. Main sequence stars make up about 90% of all the stars in the universe, ranging in mass from about 1/10 to over 200 times that of the Sun. These stars are like the typical employees in a company, showing up every day, doing their job quietly, and lasting for millions or even billions of years. Red giants and white dwarfs. The evolutionary endgame. Stars don't stay the same forever. They evolve. When a main sequence star runs out of hydrogen, it begins to fuse helium, transforming into a red giant. These stars can grow large and appear more orange or reddish due to their cooler surface temperature. The transition to a red giant phase can take millions of years, and as the core shrinks and heats up, the outer layers expand, becoming luminous and less dense. Eventually, the outer layers are expelled, and the remaining core cools to become a white dwarf. White dwarfs are stellar remnants that glow faintly from residual heat and can persist for billions of years. Think of white dwarfs as the retirees of the stellar world, done with the fusion job but still glowing due to the warmth from years of hard work. In about 10 billion years after its time as a red giant, our Sun will ultimately become a white dwarf, completing its life cycle. Neutron stars and pulsars, the eccentric ones. When a massive star goes supernova, it can leave behind a neutron star. These are incredibly dense objects, where a single teaspoon of neutron star material would weigh about 1 billion tons on Earth. If these neutron stars spin rapidly, they're called pulsars, emitting beams of light that sweep across space like a lighthouse. Neutron stars and pulsars are often the remnants of stars much more massive than the Sun, which means they've undergone catastrophic supernova explosions. Despite their small size, typically only about 20 kilometers in diameter, neutron stars have immense gravitational fields. They don't contribute much to the night sky's color, but they do provide a spectacular display for radio astronomers, as their beams can pulse at intervals of milliseconds to seconds. How stellar chemistry affects color. Stars are mostly hydrogen and helium, but trace elements like sodium, magnesium, and iron can give them subtle color differences. Spectroscopy allows us to determine these elements based on the light they absorb or emit. This is similar to how a chef adds spices to a dish. Each element gives the star its unique flavor and color. Hydrogen, the universe's most abundant element, tends to give stars their bright emission lines, while iron can create dark absorption lines in the spectrum. The presence of certain elements can also influence a star's temperature, affecting its overall color. For instance, cooler stars with higher concentrations of metals often appear red or orange, while hot young stars with less metallic content shine blue. The life cycle of star colors. As stars evolve, they change color. A protostar starts with a reddish glow due to cooler temperatures during formation. Once it starts fusing hydrogen, it usually turns blue or yellow depending on its mass. During the red giant phase, a star expands and cools, shifting its color to red. It's like watching a person grow. Stars start cool, heat up during their prime, and mellow out in their old age. The changes in a star's color are driven by alterations in its core composition and temperature throughout its life cycle. Our Sun is about halfway through its life as a yellow main sequence star and will eventually grow into a red giant, a transformation that will significantly change its color and luminosity. Why we don't see green stars? If all colors of the spectrum are possible, why don't we see green stars? The answer lies in how our eyes perceive light. Stars that would technically be green emit a broad spectrum of light that ends up appearing white to us. This phenomenon occurs because their peak emission falls in the green range of the visible spectrum, but they also emit plenty of red and blue, which combine to give the impression of a white star. The interaction of these different wavelengths effectively cancels out the green appearance. If the stars were in charge of fashion trends, green would definitely be the new never happened. But that doesn't mean these stars aren't out there. They just don't look green to us. Redshift and blue shift. Stars on the move. Not only does the color of a star tell us about its temperature, but it can also tell us if it's moving towards or away from us. When a star moves away, its light is redshifted, meaning the wavelength stretches and it appears more red. If it's moving towards us, the light is blue shifted, meaning the wavelength is compressed and it appears bluer. This phenomenon is the cosmic equivalent of the Doppler effect, where the sound of an approaching ambulance changes pitch. In the same way, stars flex their velocity by shifting shades, providing astronomers with vital information on the star's motion, and subsequently, the dynamics of our galaxy and universe. Thanks for joining me on this stellar journey through the cosmos. If you found this video enlightening, make sure to hit that like button and subscribe to the channel. Don't forget to ring the bell so you never miss an adventure across the universe. Stay curious and keep looking up.